Okay, today we're going to talk about inverses. Now, an inverse function undoes what a function does. Let me give you an example. Suppose I have a function that takes every x number and multiplies it by 3. Well, then the inverse, and we use a little -1 exponent to denote inverse, would take that answer, and what's the opposite of multiplying by 3? It would divide it by 3. If you plug a 6 into my original function, you get 3 times 6, which is 18. If you plug an 18 into the inverse, you get 18 divided by 3, which is 6. I started with a 6. My function turned it into an 18. The inverse turned the 18 back into a 6. Let's do another example. Suppose I have a function that takes every x number and adds 4 to it. The inverse, what's the opposite of adding 4? Would take every number and subtract 4 from it. If you plugged in a 7, you would get 7 plus 4 is 11. And if you plugged an 11, you would get 11 minus 4, which is a 7. Pretty simple idea. My function turns an x into a y. My inverse turns a y back into an x. Now, a couple of things which seem intuitively to be functions, but which are not, are x squared and the square root of x. We intuitively think of those as being inverses, but they are inverses only if I prohibit x from being negative. If you plug in a 6, you get a 36. You plug in a 36, you get back out a 6. But what if I had plugged in a -4? I'd get out a 16, positive. When I plugged in the 16, I'd get out a +4. So squaring and square rooting are kind of like absolute value. In fact, some books define the absolute value of x to be x squared and then the square root. Let's look at some sample questions. If my function turns a 3 into a -1, then my inverse would turn a -1 into a 3. If my function turns a 2 into a 4, what do you think the inverse would do? It would turn a 4 into a 2. If my function turns a -6 into a 0, what do you think the inverse would do? It would turn a 0 into a -6. In terms of ordered pairs, functions just flip them. It takes the x and turns it into a y, takes the y and turns it into an x. Let's look at this pair. My function took a -3 and turned it into a 2. The inverse would take a 2 and turn it into a -3. The inverse would take a 2 and turn it into a -3. What does my function do here? It turns a 0 into a -3. What would the inverse do? The inverse would turn a -3 into a 0. My function turns a 2 into a 0, so by extension, the inverse would turn a 0 into a 2. Here's one that looks complicated, but only because of the fraction. This says my function turns a 4 into -3/5. What do you think the inverse would do with -3/5? Of course, it turned it into a 4. Let's look at that idea a little deeper. Now, suppose I gave you two functions, And I wanted to see, well, is it possible that these two functions are inverses? I'm not going to prove yet that they are. I'm simply asking, is it possible that they are? Now, if I take this value 11 and plug it into f and get an answer, and then take that answer and plug it into g, if they're functions, what am I going to get? I'm going to get an 11. If I started with an 11 and plugged it into a function, then plugged that into the other function, if they're inverses, I better get back an 11. Well, if you plug 11 into this, you get 4 times 11 minus 5 over 3, which is 4 times 6 over 3, which is 24 over 3, which is 8. My function turned 11 into an 8. So if these two are inverses, what should this second function do with an 8? It should turn it back into an 11. Let's see. 3/4 times 8 plus 5 is 24/4 plus 5 is 6 plus 5, which is 11. So based solely on the values of my function and the composition of that function, I started with 11, turned it into an 8, then turned that 8 back into an 11. Based solely on that idea, yes, it's possible. I have not shown that it is inverses or that they are inverses, but simply that it's possible based off what they do with 11. Starting with the 5. In order for the answer to be yes, what should I end up with? 5. If I end up with anything else, then the answer is going to be no. Let's plug a 5 into this, and I get 2 times 5, which is 10, which is 13. So I plugged a 5 into here, and I got out a 13. I'm going to ask you to tell me that, and that on a test. Now, if I plug the 13 into this, I get 13 minus 3 divided by 2, which is 10 divided by 2, which is 5. So I started with a 5, I've got a 13, and then turned the 13 back into a 5. So based off that and based only on that, not on anything else, based only on that, is it possible that they're inverses? Yes. When would this be no? When the number I started with and the number I wound up with were not the same. Now we're going to ask you to find the inverse of some functions. And this first one's pretty obvious. What's the opposite of adding to? Subtracting to. How do I show that mathematically? Well, if I wanted to solve this equation for x, I would have to add -2 to both sides of the equation. And then if I change this to x and change this to the inverse, I have found the inverse. Algebraically, that's how you do it. You solve the equation for x and then change the names. Algebraically, how would I solve that for x? Well, I would divide both sides by 3. And those 3's would cancel, and I'd have x. Now let's do a name change. Let's call that x and call that inverse. Remember, the -1 power is the inverse, and I have found the inverse of this function. Well, this one's a little more complicated, but the idea is the same. I'm going to solve for x, and I'm going to start by multiplying both sides by 2. Now, still looking to solve for x, so I'm going to add 3 to both sides. And finally, to solve for x, I'm going to divide both sides by 5. And to complete the inverse, I'm going to do the name change, 2x plus 3 over 5 equals inverse x. Let's test this and see if it works. Let's plug in a 7. Well, that's going to be 35 minus 3 is 32, divided by 2 is 16. Let's plug a 16 into this. That's going to be 32 plus 3 is 35, divided by 5 is 7. You didn't have to do that last step. I was just testing it. How do I solve the inverse? I solve for x. And the first thing I'm going to do is add negative 5 to both sides of the equation. There are two ways to go from here. The easiest way is just multiply by the reciprocal. And let's do a name change. You could have multiplied both sides by 3 and then divided both sides by 4, but multiplied both sides by 4 and then divided both sides by 3. But I just like to use the inverse. It's quick and easy. Now, this is not a function. It's a set of ordered pairs. And we know that the inverse turns the y into the x. The inverse turns the y into the x. The inverse turns the y into the x. Now, I want to introduce a little bit of an idea. It's a little complicated, and this is kind of setting the groundwork for what we're going to do next. And we're going to talk about the inverse of raising a number to a power. We're going to talk about the inverse of raising a number to a power. Y'all remember those problems we had, like 32 to the x equals 16? How do you undo raising to a power? What we did was convert them to a common base. But we're going to learn how to solve that when I don't have a common base. What if this had been 25 instead of 16? Well, now I got a problem. They're not a common base, so I can't cancel. And the operation of inversing a power is called a logarithm. The inverse of a logarithm to a base is a base to a power. And there are a couple of things that have to be defined here. For example, you can't have a base of 1. Because 1 to any power is always going to be 1. You cannot have a negative number in here, because then what you got would depend if your x were positive or negative or odd or even. You could get more complicated there. So we're going to say that b cannot be 1, and both y and b have to be functions, have to be positive. Do you notice anything about those? They both have a b on the left. Just kind of swap the places of the y and the x. And that's one way to think of it, that when you're converting from a logarithm to an exponent, all you have to do is swap, lose your log, knock the log off the frog, and he hops to the other side. All right, so what did we just learn about logarithms? That logarithms to a base are the inverse of a base to a power. Now this question says, remember, logarithms always equal an exponent. Logarithms equal an exponent. Logs equal an exponent. And what this question says is, what exponent on 5 gives me 5 to the third power? Let's write that down. What exponent on 5 gives 5 to the third power? What exponent do I have to put on 5 so I get 5 to the third power? Well, the answer is 3. 3 is the exponent I would put to get 5 to the third. Algebraically, I can say that a log base and a base cancel. Assuming they meet all the other requirements, a log base and a base cancel. Now, this question says 2 raised to whatever power it takes to give me 64. And the answer is 64. Remember, the base and the log base cancel. Look here. Look here. The base and the log base cancel. That becomes a simple first order equation. That becomes a simple first order equation. That should be x minus 7. That should be minus 7. X is 13. Once again, the log base and the base cancel. And if you remember from our board that 128 is 2 to the 2, 4, 8, 16, 32, 64. 2 to the 7th power. And so log 2 of 2 to the 7th cancels. I knew what it was, but I was helping y'all remember. And that becomes a first order equation. Or 5/2 or 2.5. Now, because the inverse of a logarithm to a base is base to a power, and remember that when you have a logarithm, it always equals the exponent. A logarithm equals the exponent. That tells me my exponent has to be 2. How could I arrange a 3 and a 9 with an exponent of 2 to make that a true statement? Well, we would say 3 squared equals 9. Or we could say as a sentence, the exponent on 3 that gives 9 is 2. This says the exponent on x that gives z is y. Because logarithms equal an exponent, I know right here my exponent is going to be y, and the base is x. Like we talked about a minute ago, you can kind of think as knocking the log off the frog, and those two swap places. Now looking at this says 2 to the 5th power equals 32. But because I know that logarithms are exponents, my answer is going to be 5. Because the logarithm always equals the exponent. The base is 2, and so the 32 goes there. Or we could put the log back on the frog, and these two swap places again. That's kind of an easy way to remember it. It's not a good explanation of what it does, but it's an easy way to remember it. Now, looking at this, we know that the logarithm always equals the exponent. So what's the logarithm going to equal? N. And what is the base? G. So the P has to go there. Or you can think about it. We used to have a teacher, Miss Hutch, who taught this. Put the log on the frog, and these two swap places. Let's look at some sample test questions. I'm going to solve this for x. So I'm going to start by multiplying both sides by 5. I'm going to continue by subtracting 7 both sides. And then we're going to do the name change. So my inverse is 5x minus 7. How could we test? Well, let's plug a number in over here. I'm going to plug a number in that when I add 7 divides by 5 nicely. I'm going to plug an 8 in. And that's going to give me 15 divided by 5, which is 3. If I plug a 3 in here, I get 15 minus 7, which is 8. So based on that, it's possible that they're inverses. You don't have to check. I just am. Okay, I want to solve this for x, and I'm going to start by adding -1 to both sides of the equation. And there are lots of ways to do it, but the way I like to is simply multiply by the reciprocal, which I think I forgot to put parentheses on the other one a minute ago. I need to go back and do that. And that becomes 3/7 f of x minus 1 equals x. I'm going to go back and see where that one was. I forgot to do that on. Yep, that should have been 4/3 the whole thing. And so that should have been 4/3 of the whole thing, not just 4/3. Whoops. Go back and change that in your notes. I'm too far into the video to start over again. All right. What does my function do with a 2? It turns it into a, well, that's not a question. My question is, what does my function do with a 1? My question takes a 1 and turns it into a 2. My function takes a -3 and turns it into a 1. What does my inverse do with a 1? My inverse takes a 1 and turns it into, I'm going to change colors there. My inverse takes a 1 and turns it into a -3. My inverse takes a -3 and turns it into a 5. Let's go to the next page. All right, this is where we're going to test to see if they're possible inverses based solely off the values of what I get when I plug it in and plug the answer in. So let's see. If I plug a 4 into f, that's going to become 2 minus the square root of 5 plus 4, which is 2 minus the square root of 9, which gives me -1. Now, if we plug -1 into this, I have 2 minus -1 squared minus 5, which gives me 3 squared minus 5, or 9 minus 5, which is 4. So I started with a 4, turned it into a -1, and got out a 4. So based on that, are they possible? Not are they definite, but are they possible inverses? The answer is yes. Why? Convert to exponentials. Since the logarithm always equals the exponent, I know that 5 is going to be my exponent. And if I knock the log off the frog, the base is w. 5 becomes the exponent, and it equals k. So we would say w to the 5th equals k. Once again, this is an exponent. I want to convert it to a log, and we know that the log always equals the exponent. The log always equals the exponent. And the base is 5, so the w and the k swap places. Last page. What is my function doing? My function is turning a 9 into a 4, so my inverse would turn a 4 into a 9. My function turns a -2 into a 3. My inverse would turn a 3 into a -2. And my function turns a 5 into a -8. My inverse would turn a -8 into a 5. From this chart, what does my function do with a 5? It turns it into a 0. By extension, the inverse is going to turn a 0 into a 5. My function turns a 0 into a -2. By extension, my inverse is going to turn the -2 into a 0. My function turns a -2 into a 5. By extension, my inverse is going to turn a 5 into a -2. This problem says my function turned a 4 into a 5. What would the inverse do with a 5? It would turn it into a 4. Well, good luck to y'all. I'm going to put some online test prep problems in Canvas again. Y'all stay on top of these. I'm going to try to figure out how we're going to do our exam. And I really hate not seeing y'all. But good luck with this, and let me know if I can help.